Hello everyone and a very good morning to all of you. Distinguished delegates, presenters and participants from SAARC member states and other regions around the globe. Ladies and gentlemen, I'm very thankful to all of you for joining us in the SAARC webinar on use of solar energy in water desalination. My name is Muhammad Umar Mukhtar and I am working at SAARC Energy Center as Research Fellow Energy, Transport and Environment. I shall be moderating today's SAARC webinar as well as presenting the aim of this webinar opportunities and challenges linked with the use of solar thermal desalination and purification. Any policy, regulatory or project-based initiative. This webinar will also help SEC link up with experts and the professionals of the SAARC region by developing strong networks with the distinguished experts in the field. In the long run, through such insightful webinars, SAARC Energy Center aims to strengthen its bond with global experts and SAARC professionals. South Asia is a water-stressed region, and a water crisis is increasing for many regions in South Asia. Apart from Bhutan and Nepal, South Asia's per capita water availability is already below the world average. Bangalore, Karachi and Kabul are among the 10 cities in the world that are on the verge of an imminent water crisis. In fact, according to Asian Development Bank, water supply in India may fall 50% below demand by 2030. But with abundant solar energy potential in South Asia, a viable economic case could be built for solar, thermal and solar PV based desalination. Therefore, this webinar will be an thermal desalination as well as PV desalination of seawater, As solar thermal desalination is in its early stages with a few projects recently established, therefore the webinar will not only provide theoretical knowledge but will also share the important learnings from those recent projects and will aim to share with the SAARC professionals the solutions to commonly encountered problems during those projects. The possible participants of the webinar would be from relevant government departments, research organizations, academia, associated industry and entrepreneurs, etc., specifically from South Asia. I'm also grateful to our Deputy Director, Dr. Shoaib, who is present here in today's webinar. I'm also grateful to our panelist, Mr. Bilal Hussain, Research Fellow Power at SAARC Energy Center. Dear participants, you will have the opportunity to ask questions to presenters by typing your questions or clicking to the raised hand option into the attendees panel of the main window of GoToWebinar software. You may also send in your questions at any time during the presentation. We will collect these questions and address them during the question and answer session at the end of each presentation. Additionally, you will also have a chance to share your views at the end of the webinar or through emails. Now, moving on to the presentations. Our panelist, Mr. Bilal Hussain, is an electrical engineer from UET Lahore and finished his master's on renewable energy management from University of Applied Sciences, Cologne, Germany. He has served in National Transmission and Dispatch Company, Pakistan for around 5 years as assistant manager in several directorates, notably Central Power Purchase Agency and Power System Planning. He has an extensive experience in grid system engineering, power system planning, and energy purchase agreements. On academic front, he has a publication to his name and has executed several model-based research projects focusing on energy technology and cost factors in multiple countries. He holds a strong grip on the modules, and his areas of interest are regional energy cooperation and dialogue, sustainable power systems, and renewable energy technologies. I would move towards Mr. Bilal Hussain. So, Mr. Bilal, can you hear me?
Yes, thank you, Umar. I can hear you clearly. Can you see my screen and can you hear me now?
Yes, your screen is visible. You may please go ahead.
Okay, perfect. So, thank you, Umar. Good morning, everybody. I am Bilal Hussain. I am a research fellow power at SAARC Energy Center, as you have already been briefed about me. In this presentation, I will be discussing the mature, commercially viable solar desalination technologies, which are currently being under focus for the small island states. So the scheme of the presentation would be pretty simple. I will just start with a brief context of the drivers which are motivating to use renewable energy-based desalination in islands. Then I'll be briefly going through the desalination technologies and their peculiar characteristics which enable us to combine them with the available renewable energy sources. And then we will have a brief overview of the market segmentation of renewable desalination. And then I will go through a little case study, which is basically an IRENA study being done in 2015 on small islands, where we will find some very interesting graphs on the economics of different RE desalination solutions. In the end, we will just collect some takeaways and a little bit outlook in this regard. So starting with the island context, the pretty basic stuff is that islands are surrounded from everywhere, the vast oceans. That indicates that they are isolated from large inhabited areas, which indicate that in cases of emergency, there has to be the fresh water sources available for the inhabitants, and therefore either the infrastructure should be there for providing that fresh water, or in terms of the storage, some imported fresh water or other sources must be available. The second thing is the topographical limitations of island states generally being surrounded by the salt water around the groundwater storages or the freshwater resources. The lenses and the lakes are always prone to saltwater intrusion. And this fact becomes even more dangerous in times of climatic extremes like cyclones or typhoons. And this adds to further complexity that the climate change is affecting the island states more in respect to increasing the extreme effects of the climate extremities. And on top of that, the seasonal variations are already hitting the supply demand mismatch in islands. One particular aspect is the tourist seasons, which can increase or decrease the water demand significantly. Some islands may have dry spells in in winters, and floodings in summers time, which can badly affect the supply demand management. One other aspect is generally the in the islands. Generally, the low-lying areas of the islands do not have pretty good groundwater resources, and the very steep island areas generally find a lot of water runoffs right after the rainfall, and it's very difficult to even store the rainwater. Under these challenges, the basic option for island states is to either import water for its needs, or to install the desalination plants based on the conventional fossil fuel technologies. In that case, even they have to import more fossil fuels. So that leads the basic motivation of why the renewable energy desalination becomes crucial for island states. The prime factors are, of course, two. The one is the fuel costs reduction, because renewable energies may have the initial capital cost, but they are essentially having no fuel costs, which can actually, in effect, give more chances of economic development in the island states. Then the second prime factor are the reduced imports of the fossil fuels. That gives the security of supplies and decreases the dependence on the imported fuel source. Now, quickly moving to the next stage. I will, in the couple of slides, I will give you a brief overview of the mature technologies which are actually available in the pilot form or the commercial form around the world. Firstly, if we segregate in the category of thermal-driven desalinations, the first category is the multi-stage flash desalination, which is essentially based on the principle of evaporation. The prime principle of operation is that the cold feed of the saline seawater comes through the low pressure flash chambers. It is heated, and once the heated fluid goes into the low pressure flash chamber, it evaporates very quickly and condensates onto the collecting vessels. Of course, the more number of stages you add for evaporation, the more quality of water is improved. But generally, the multi-stage flash or multi-effect desalination, or any kind of technology which is working on the evaporation, it produces better water quality in terms of lower salinity. One particular factor of multi-stage flash is that the top brine temperatures are around 112 degrees centigrade. This temperature is not so low, but not so high as well, and it qualifies these kind of solutions to work with the concentrated solar plant steam feed. Of course, that adds a little bit penalty of having no possibility of generating electricity from that steam. But going on to the next technology type, which is the multi-effect desalination, that drawback is actually compensated. The principle is same, of course, evaporation, but in a slightly different mode of operation where the cold feed from the seawater is sprayed onto the motive steam pipe in the first stage of low pressure chamber, which evaporates the clean water from the feed input, and that vapors are collected in a tube, and in the next stage it appears it basically evaporates the further cold feed of the saline water. So the number of stages you add is basically increasing the quality of the water, clean water output. um, the good thing about this technology is that the technology requires medium operating temperatures of around 70 degrees centigrade. And at this temperature, the low grade waste heat from the concentrated solar plants can be utilized. So generally, the low grade heat is very inefficient in terms of producing electricity. And if it is used in terms of desalination, then it's a better utilization of resource. And that adds to the benefit of multi-effect desalination solutions that we generally consider the waste heat that is going to be wasted anyways to be used in desalination. Therefore, it's essentially a free resource. Reverse osmosis, and this solution forcing the water onto the membrane, and with that pressure, the clean or drinkable water is separated from the saline water remains on the other side. Because it requires pressure, it's that almost a major portion of electricity to water salinity, because that is basically indicating the osmotic pressure that is needed to operate such plants. And the available technologies today for commercial operations, these plants are sensitive to energy fluctuations, which is in fact an area where it's a big barrier for connecting such kind of plants with the conventional renewable resources without storage infrastructure. Therefore, more research and development is happening on this side. And if breakthrough occurs and if it's more flexible, it will help in further expansion of these kind of technological solutions. The other type of electricity driven desalination technique is the electrodialysis, which is in fact a principle quite similar to two opposite charge electrodes are given a DC electric supply, and it does the separation work for clean water and the saline water. Electrodialysis, of course, has very limited application, and it's generally feasible for brackish water applications. But one peculiar fact of the operation on DC supply indicates that we can directly integrate such solutions with photovoltaic sources. In addition to that, there are several other solutions which fall under different thermal or electricity driven categories. One is to use a mechanical or compression system, which is in fact compressing the clean water and vaporization using the pressure difference. This mechanical or thermal vapor compression system requires energy as well, because it requires a mechanical profile, and more feasibility is there to integrate such solutions with offshore wind. The other technology is a membrane distillation, which is sort of a hybrid between a membrane technological option and a direct distillation technology. and a thermal generation, then the terms of vaporization. Particular benefit in terms of integration with renewables is that they operate on a lower feed water temperatures of 60 to 90 degrees centigrade. That means that the waste heat from concentrated solar plants can be effectively utilized in operating such solutions. Then of course, this membrane distillation technology is quite insensitive to the energy fluctuations, and only a few pilot projects are there in the world at the moment operating in this regard, and it's generally applied on a lower scale of size, roughly around 10 meter cube per day. Then the other technology is the open cycle ocean thermal energy conversion based desalination, which takes the benefit of the primary phenomena of temperature gradient as we move from the surface of ocean downwards. Generally, in the oceans, we can find a gradient of 25 degrees centigrade in the depth of 500 to 1000 meters. The principle of the technology is basically the low pressure infeed evaporates by the relatively hot water from the upper ocean layer, and then it expands in a turbine and condenses using the cold water from the lower layer. This technology is pretty much in the R&D stage at the moment. The efficiency is very little, just 3 to 5%. That indicates a lot of seawater has to be processed to get a certain amount of drinkable clean water. But if this kind of technology matures up to the commercial stage, it holds quite a benefit for island states. The other technology is a freezing option, which in fact principally dependent on freezing a certain volume of water where the dissolved salts get separated and can be rinsed out. Freezing is generally less energy intensive. It's almost takes 15% of the energy that is required for vaporization, and it can essentially work with any kind of renewable energy, and in fact it can work with solar thermal as well using absorption chillers. Of course, it requires more energy than the reverse osmosis based plants, but the freezing technology is also under R&D today. So in this slide, I will just give a brief overview of the market segmentation worldwide, and in particular in the small island states. At the moment, you can see that most of the desalination market is dominated by reverse osmosis plants. Worldwide, its percentage share is 66%, while in the islands it's more, it's roughly around 80%. And the prime reason for the dominance of reverse osmosis plants are their scalability and modular ability. Reverse osmosis plants can be actually constructed in a small scale, medium scale, and large scale, and generally the islands usually find applications in the small to medium scale, in which this technology is pretty mature on the commercial basis. Generally, islands would go for the small scale options, which roughly cover around 10 to 1,000 cubic meters of water production per day. And the islands where we have more densely populated communities and a little bit central infrastructure, the medium scale desalination plants are also available in the range of 1,000 to 100,000 cubic meters per day. Of course, all of these technologies at the moment are dominantly working with the conventional fossil power. After the reverse osmosis technology, the dominant technology is the multi-stage flash desalination, but in the island states, the multi-stage flash and multi-effect desalination are quite at par with each other. And of course, this electrodialysis also finds more applications in the island states because of abundant availability of brackish water. When we talk about the possible combinations of renewable energy sources with different desalination technologies, then I can have I can show you actually a very interesting graph on the left side, which segregates the different combinations in terms of the indirect and the direct usage of solar. In terms of the direct usage of solar, mostly the unconventional types like solar still or humidification or dehumidification technologies are available, and they are available long time, but their scalability is very small, and they are used only for temporary or for remote communities. And for very small scale applications. For the indirect types, we have mainly photovoltaic and solar thermal. And photovoltaics finds applications in respect to reverse osmosis desalination plants, electrodialysis plants, and mechanical vapor compression plants. Um, it's because the photovoltaics are producing electricity only, and the reverse osmosis and electrodialysis are basically electricity-driven desalination applications. Therefore, it's more feasible to connect, and there is no role of heat here. But the reverse osmosis plants definitely require more stable supply sources. Therefore, integrating photovoltaics directly to RO plants without storage is still under R&D. On the side of solar thermal based desalination plants, the variety is more. Solar thermal plant basically produces electricity as well as heat. Therefore, it ideally combines with the multi-stage flash and multi-effect desalination, where both of the resources are utilized. But they can also be used in membrane desalination or thermally driven vacuum compression desalination, and also in reverse osmosis plants. When we talk about the maturity of individual technologies, on the graph on the right side, we can see that on a very small scale or the small scale, the photovoltaic fed reverse osmosis plant supplied with some kind of backup, either a battery or a grid, are the ones which are at the top level in terms of maturity. Small scale applications are already running on a commercial basis, and uh, the medium scale is generally available as a demonstration project. Then comes the multi-effect desalination technologies, which are basically fed through the concentrated solar power plants, and it's basically under the R&D on the medium scale, which also has the promising price favorability. But in the small scale, we can see some demonstration projects around the world as well. I already indicated that an off-grid photovoltaic fed reverse osmosis plant without a battery is very favorable in the future, but because the present RO technologies require more reliable and constant based supply source, therefore this kind of plant is in research and development, and if it has the potential of commercialization, it will give a great benefit to the island states. So if we summarize in terms of fewer technological combinations, I would rank photovoltaic fed reverse osmosis as the most commercially viable solution for the island states. It gives lower cost of water production. We have number of commercial plants and pilots already running around the world, and it of course needs storage of electricity or a grid connection to avoid any supply fluctuations as per the present technology available. Then on the second level, I would rank the concentrated solar power plant based reverse osmosis. It is generally more efficient than the solar thermal multi-effect desalination when we talk about the medium scale. It is, of course, more suitable for the larger scale as well, but it is at present in the research and development and demonstration phase. Then in the third level, it comes the concentrated solar panel-based multi-effect desalination. it finds favorability when the water salinity is high in an area, because with higher salinity it requires more push against the natural osmotic pressure. Therefore, the reverse osmosis plants require more energy in this kind of situation. Of course, the multi-effect distillation technology has the flexibility bonus and also this provision of simultaneous use of heat and electricity, which is particularly very beneficial for the energy system as a whole in terms of optimum utilization of all kind of resources. So now I will present a few slides on the cost trends, which I have just taken primarily from an IRENA's assessment report on small island states, which was happened in 2015. The report actually compared the renewable energy desalination solutions with the fossil-powered desalination. Comparison was basically done on the levelized cost of water production for a scale of plant ranging between 250 to 2000 cubic meters per day. In this slide, you can see two graphs. The first one is actually showing the levelized water cost for reverse osmosis plants producing 250 to 2000 meter cube per day. We can see that general electricity supply cost in islands can vary from $0.2 per kilowatt hour to $0.5 per kilowatt hour. And against that variation, we can see the levelized water cost can be between $1.5 per meter cube to $3.3 per meter cube. Of course, this is the conventional fossil-based power grids we have in today's world. And on the right side of the graph, you can see the levelized water cost of multi-effect desalination plant with electricity prices in the same range. Here, of course, the horizontal axis is shown in terms of the diesel fuel cost price just to indicate that the fuel cost rise can have a bigger effect on, can have a significant effect on the water cost for the islands. It's also kind of a situation where it becomes a political problem as well. So, for example, for a diesel cost of $1 per liter, we can say that this kind of technology will cost the water production around $5 per meter cube, but the same fuel cost rising about 30%, then it can also have an increment effect of $1.5 on the price of water production. So the first comparison on this slide is basically a grid-connected photovoltaic-fed reverse osmosis solution. The IRENA report assessed two types of plant configuration. The first type is the photovoltaic providing 7 hours of production, and the rest is being fed through the electricity grid. And the cost is calculated using the weighted average approach. And the graph indicates that under this configuration, the cost of water production is roughly around $2.4 to $3.3 per meter cube, which we can see against the reference status quo to be quite comparable. And because it has the other benefits from the climatic perspective, the renewables are already competing with the conventional sources in terms of desalination applications. The other configuration of the same plant is 24 hours supply from photovoltaic with the battery storage provision, and it's an off-grid solution. Under this category, the report assesses that the price of production of water increases almost twofolds, and it roughly comes in the range of $5.5 to $5.8 per meter cube. So therefore, the economic financial viability of this configuration is still requires much more improvement. The second solution that was assessed in the IRENA's report is the solar thermal fed reverse osmosis plant. When we compare it with the reference status quo, we can see that the rough range of water production cost for such kind of combination comes from $2.5 per meter cube to $3.3 per meter cube. Of course, with the increasing norms irradiation of sun, the price favorability increases, and that increases the economic viability of this kind of solution over the status quo-based solutions. Sorry. So the last combination that I would present in this presentation is the concentrated solar plant fed to multi-effect distillation plant. And of course, you can see that against the status quo fossil-powered desalination solutions based on the reverse osmosis, the price comparison doesn't indicate any favorability of this kind of scheme. We can see roughly the range of water production costs are around $5 to $7 per meter cube. But let me remind you that in the previous slide, I showed that the conventional fossil-based power plant feeding to a multi-effect distillation also comes around this range. So if I go back to that slide, I can show you slightly. So in this graph on the right side, you can see the range of water production from the status quo electricity sources based on multi-effect distillation is from $5 to $8.5 per meter cube. So when we see the graph of concentrated solar-fed MED system, in many cases it becomes more favorable. Of course, the plant design has this critical parameter of storage, which can significantly affect on the cost performance of such kind of plant. So if I summarize the different technologies considered in the report, this graph can actually show you a very good exposure, a very good picture of the price comparison of different solutions which the report has assessed. When we start with the waste heat based multi-effect distillation, and that's the waste heat coming from some conventional fossil-based power plant, it's the most favorable in terms of cost performance. But then comes in terms of renewable, the photovoltaic fed reverse osmosis plants, which has a favorable cost range from $1.8 to $2.8 per meter cube, which is fairly comparable with the status quo solutions of reverse osmosis in the islands. Then after that, more promising are basically the wind-fed reverse osmosis plants or the concentrated solar plant-based reverse osmosis plants. At the moment, the multi-effect distillation systems fed through renewable sources are higher in terms of their price performance. But when we consider the quality of the water coming out from such plants, it's on the higher end because they are based on the evaporation principle. So if I summarize the few takeaways from this case study and a little bit outlook for future, the first point would be that declining energy storage costs will definitely favor in more expansion of the renewable energy-based desalination in future, and particularly the photovoltaic fed reverse osmosis solutions. In future, flexible reverse osmosis desalination solutions will attract more investors and energy companies. It's particularly important in context to energy companies because the renewables always require more flexibility in the grids. And if the distillation plants can provide that flexibility, I would think that the resources will be more optimally utilized. Then the IRENA report gave a very interesting area for exploration, that was refilling of the overexploited groundwater resources with the desalinated water coming out from the renewable energy distillation solutions. And when we focus on these kind of niche applications, I think many of the renewable desalination solutions are favorable. Then the bigger size of the renewable desalination plants are generally cost effective, especially when they are operating on the low temperature waste heat. And in this regard, the multi-effect desalination technology is much more dominant. Of course, asides the maturing technology options, the expansion of renewable energy desalination solutions requires a better training and education facilities, information sharing on the best practices, and of course, the functioning supply chains. Without that, the expansion of renewable energy desalination will be very slow and may not be returning in terms of future uh, challenges of climate change. So that's all from my side. Uh, Thank you very much. So over to Omar, please.
Thank you very much, Bilal, for a very comprehensive presentation on the use of solar energy in water desalination, especially in the context of island states. We have one question here from the participants. The question is, what size of RO plants are generally recommended in island states? Do you have an answer for that?
Uh, uh, Generally, it depends on the density of population within an island. If an island is densely populated and there is sort of a central infrastructure, a plant size in the medium range, which is roughly 1,000 meter cube per day to 10,000 meter cube per day, is much more frequent. But in islands where the population is not very dense and there is no central infrastructure, generally the smaller scale of plants are more frequent, roughly in the range of 20 meter cube per day to 1,000 meter cube per day.
Thank you. Secondly, I wanted to ask regarding the charts which you presented earlier. In those charts, you considered the price of diesel as a comparison with the CSP. Basically, what we are saying is that the diesel-based generators are mainly used in the island states. So that is why we are going for diesel, or is there some other reason? What I assume is that Maldives, it's a SAARC member state, and it uses there's a lot of consumption of diesel in those island states. Is this the reason why a comparison for diesel is presented?
Hello?
Hello, can you hear me, Bilal?
Yeah. I could hear you till Maldives. After that, I couldn't understand.
Okay, so you know that Maldives, it consists of so many islands, and the diesel consumption in Maldives is very high. In
Mhm.
your charts, you presented a comparison of the price of solar desalination as a factor of diesel price. Does the IRENA report it only consider diesel in its calculations for the small island states?
Yes, in fact, in the island states, most of the fossil source of energy is coming through the diesel-based solutions. But of course, it will have a little bit mix from the gas and other oil products, but it is majorly driven based on the diesel solutions.
Okay, so we have one question from a participant, Miss Anila Fatima. She's asking, do you have any knowledge of any small-scale water desalination plants in Pakistan using solar energy?
Um, I think there is one which is already developed in this new coastal city we have, but I am not confirmed whether it's based on the solar-fed reverse at the moment. But there is a potential for Gwadar to build such kind of plants.
Just to expand on this question, what I know is that in around like 1970s and 80s, there was an effort by the government of Pakistan to introduce solar-based desalination technology in Gwadar, because always has been it lacks proper water access. PICRIT was given the mandate to provide desalinated water using solar energy to those communities living in Gwadar. But I don't know of the current status as well.
Yeah.
So yeah, so we are done with the questions here. Dear participants, if you have any more questions, you may you please feel free to send your questions, and we will direct these questions to our expert. Bilal, thank you very much for your comprehensive presentation. We'll move on to the next presentation.
Yeah.
The next presentation is basically an overview of the current solar desalination technologies. So I'll be giving this presentation. So basically, the purpose of this presentation is to give you a holistic overview of the solar technologies which are currently, in the world. There are basically the two main types of solar technologies which are used for desalination purposes are the solar thermal and solar PV based technologies. So in this, as a part of this presentation, we'll be going through both of these technologies and how they can be integrated and how they are actually integrated with different kinds of solar desalination. We will also be going through the economics of the solar desalination regarding different technologies, and finally we would be discussing a case study for solar thermal desalination. So, the structure of the presentation, first of all, the general information regarding desalination would be discussed, why desalination is important, the rationale for introducing and using desalinated water, in the light of global water crisis, and a comparison of the technologies available. Then we will move on to small scale desalination efforts, which usually involves solar stills. As I was earlier answering Ms. Fatma Neela regarding the introduction of solar desalination by Pickrit in Gwadar. So basically, those were in the form of solar stills. That the solar still technology was introduced in Gwadar. It's a very old technology, and we will be discussing that in detail. Then we'll move on to the large-scale desalination efforts, which includes reverse osmosis, electrodialysis, multiple effect distillation, and multi-stage flash distillation. Mr. Bilal has briefly touched these desalination technologies, but I'll be explaining these technologies in greater detail. Then finally, we will be going through the implementation of solar energy, the comparative cost analysis, the technical challenges, and the case study. So freshwater resources, basically they are depleting rapidly as the global demand for water continues to increase. Because of rising demand for natural resources combined with the effects of climate change, especially in dry land and coastal inland regions, as a result, 1 out of 11 people lack access to clean water. And this is a problem for both developing nations as well as developed nations. The United Nations Environmental Programme, UNEP, it mentions in one of their findings in 2012 that 1/3 of the world's population have access to fresh water resources for their livelihood, while the rest will suffer acute water shortages by the year 2025. It means that the 2/3 of the world population would be considered water stressed. By 2025, around 1.8 billion people will also be living in areas of absolute water scarcity. In many arid regions, the surface water resources and shallow wells are being depleted at an unsustainable rate. So, drilling to access the water table is costly and it requires specialized drilling and pumping equipment. Additionally, the shallow wells and surface water resources often contain poor quality water that can be brackish and salty. So this particular scenario and case is very evident in the Middle East. The small states like Qatar, Bahrain, they have even if you manage to find the water resources below the land, those water resources are often of very poor quality, and they can be basically considered brackish water. Then consumption of poor quality water can obviously lead to adverse health effects, and almost 3.4 million people die every year from water related diseases. So the water scarcity trend is projected to increase as global population increases. Right now, human population is growing at a rate that puts stress on our current fresh water supply. Currently, global water usage is around 9 trillion cubic meters a year, and this rate is expected to increase by approximately 60 billion cubic meters more per year. As a result, we have to take care of our freshwater resources, and we need to explore new water resources, which could be in the form of water desalination. Let's have a look at the world regions which are deeply affected by the lack of fresh water. As you can clearly see in the infographic, uh, Middle East, North Africa, and South Asia are among one of the most affected regions in the world. Almost 358 million people in Africa, they don't have access to clean water. 180 million people in Southwest and Central Asia, they don't have access to clean water. This clean water also includes not having access to fresh water as well. Then 186 million people in Southeast Asia, East Asia, and Oceania region, they don't have fresh water availability, and overall, around 770 million people lack fresh water access. So, how to address the problem? We have a solution in the form of desalination. The best way to grapple with this situation is desalination, because it can play a leading role in increasing the supply of fresh water in both developing as well as developed nations. Um, let's talk about the definition of desalination. Desalination is the process by which salts and other dissolved solids are removed from water in order to produce water which is suitable for human consumption as well as agricultural purposes. Desalination not only pertains to sea and ocean water, but it also involves the removal of salts from brackish water such as agricultural and industrial waters. Today, developments in desalination technologies are specifically aimed at reducing energy consumption and cost. So, solar desalination is a technique which could potentially reduce energy consumption by desalinating water using solar energy. And there are two basic methods of achieving desalination using this technique, which are direct and indirect solar desalination. Let's have a look at the comparison of desalination for seawater and brackish water, and see that what do we exactly mean by seawater and brackish water. Generally, the concentration of total dissolved solids in seawater is 3.5 to 35 times greater than the concentration in brackish water, which means that the desalination of brackish water is significantly cheaper and easier to carry out. We need to look at the resource availability of brackish water. Generally, it is available in many nations, and the availability is inland, which means that the saline areas, the saline earth, which are affected by the salinity, they usually contain brackish water. But because the concentration is not as high as seawater, therefore it's easier to carry out desalination and much cheaper to carry out desalination for such an area. Finally, before moving towards the technology discussion of technologies, let us discuss the current status of desalination in the world. There are around 18,436 desalination plants worldwide as of 2015, according to International Desalination Association. These have a commissioned capacity of 92.5 million cubic meters per day, catering for water needs of over 300 million people globally. The desalination plants with high production capacities are mostly installed in the Middle East region. Seawater desalination in the MENA or the Middle East region uh, it's on the rise because they have an acute shortage of potable water resources. And the desalination capacity in the Middle East region represents 44% of the global desalination capacity. Currently, there are 2,800 desalination plants in the Middle East region, and it produces around 37.3 million cubic meters per day of potable water. Despite the huge capacity in the Middle East region, other regional centers of activity are also becoming very, very prominent, such as the Mediterranean Sea, the Red Sea, and the coastal waters of California, China, and Australia. The reason why desalination plants are so widespread in the Middle East region is because the countries in the Gulf region, they face the largest per capita water scarcity in the world, with an average water availability of less than 300 cubic meters per capita per year. In comparison, right now Pakistan is being talked about as a water stressed region, and we have per capita availability of around 1000 cubic meters per year. So you can well imagine the kind of stress the Middle East region is going regarding water. So desalination is very, very practical in these seas because, especially in the Gulf region, because they have lower salinity than the ocean, which lowers the energy consumption requirement. So this is also a very important aspect. If this generally the seas around the Gulf region, they have lower salinity as compared to the Arabian Ocean nearby. Now let's move on to the desalination solutions. First, we'll discuss the small scale desalination solutions for single family and small households. So the major methods of providing fresh water for inhabitants of rural areas include drilling, piping, trucking, resettlement, and desalination. In the long term, drilling for fresh water is generally preferred, but it is a very expensive activity and it requires highly technical and expensive drilling equipment. Moreover, as we discussed earlier, especially for the Middle East region, the drilling process would often lead to brackish water, and therefore it's unsuitable for human consumption. Due to the high cost of most desalination technologies and other water production techniques, use of solar still technology is recommended as the main method of desalination for both single and multi-family households. Solar stills are best utilized in situations where the demand for fresh water is very small and the land is inexpensive. Solar stills are themselves a very inexpensive technology, and they require very less technical knowledge to design and construct. And they can help promote self-reliance and enable small rural communities to develop further. The desalination technologies for larger operations have a significant capital cost and energy requirement. And for the larger the cities and towns, the European Union funded a report which assessed that the best low cost and effective desalination method for local urban areas is electric desalination. For rural areas, the recommended technology is solar still, and for urban areas, it's the solar dialysis method. Moving on to the technical aspects of solar stills. Solar stills are very, very old. It's a very old technology which dates back to the 19th century. A solar still is made of an airtight insulated basin, as shown in the picture, that is covered with tilted glass sheet, and the water is heated inside a transparent glass or plastic cover and is absorbed by salty or brackish water in the basin, so that the water is heated and evaporated. The water vapor condenses at the inner side of the glazing and evaporates at the outer side of the glazing. Basins are painted black in order to increase solar absorption, and long wavelength radiation cannot pass from the solar still through the glazing. In other words, the greenhouse effect makes the solar still look like a heat trap. A solar still needs flushing to prevent salt precipitation, and the flushing frequency depends on the quality of fresh water. Currently, freshwater production varies anywhere between 2 to 7 liters per day, and these water production variations are due to the design and geometry of the solar stills. Let us discuss the pros and cons of desalination. Desalination does not need chemical treatment in order to pre-treat the water. The disadvantages is that it has a very low production yield of 2 to 7 liters per cubic meter of covered area per day. It is not economically viable for large scale applications, and it requires a large land area if we want to size up the operations. There are different variations in solar stills. Mainly, solar stills can be classified as passive or active stills. Passive stills will use only the solar energy falling into the unit. In active stills, an external thermal energy source is added to the unit to aid heat addition to the salty or brackish water. Additional heat could be provided by a concentrating solar panel, waste thermal energy, or a conventional boiler. Uh, Another classification of solar still is based on the geometry, such as single slope or double slope glazing cover, vertical solar still, conical solar still, and multiple stage solar still. Apologies for the network disconnection. We have just reconnected. There was some issue on our end. I hope that I'm audible right now. So I was mentioning the solar still variations. So let me restart this slide. Basically, solar stills can be classified as passive or active stills. Passive stills only use the solar energy falling into the unit, while in active stills, an external thermal energy source is added to the unit to aid heat addition to the salty or brackish water. Uh, in the picture in this slide, you can see a multi-stage solar collector. In this solar collector, you can clearly see an external source of heat, which is the sun, a solar heater, which is basically a heat exchanger, and a vacuum pump, which could enhance the evaporation rate. So such solar stills basically they capture more energy, and in turn they increase the overall desalination rate of the equipment. Moreover, there are other variations which could be added to a solar still. For example, the cover. It can be made of glass or other transparent materials and can be given a number of different glossy finishes that vary in efficiency of the amount of water condensed. Moreover, additives can be added, such as solar stills use brine or other substances to aid in water absorption. The spout runoff, after the clean water falls out of the still, the spout runoff can be put through a variety of runoff techniques for further cleaning. For example, slow sand filter. Here we have an example of Aquamate solar still. Basically, it's a portable variation used for seawater and mainly used by US military and life raft survival kits. In this solar still, the clean water falls into the donut of the buoy and can be sucked through drinking tube. Moreover, we have another product called Elio Domestico. It is a ceramic pot that utilizes basic concept of boiling. The sun heats the black boiler on the top, turning it into steam, which is forced down an expansion nozzle where it condenses against the lid. The yield of this product is around 5 liters per day, and the estimated cost is $50. So these are some of the smaller applications of solar stills. If we want to scale up, we could use solar concentrators for solar stills. Depending on the need, there are three types of concentrators which we could use. These are flat, parabolic, and dish tracking concentrators. In desalination applications, the concentrated solar energy can either directly heat the water to temperatures in order to remove impurities, or it can focus the energy onto a plane of solar thermal collectors or PV panels that can then power desalination plants. In the dish type and parabolic type concentrators, the energy of the sun, it is focused onto solar thermal collectors, and then it basically uh, it speeds up the water desalination process, and this is a very good example for scaling up the solar still technology. Now we move on to the large scale solar desalination methods. There are two basic distillation processes that are currently in use globally in the use. One is the membrane distillation process and other is thermal distillation process. Within the membrane distillation process, we have the reverse osmosis and the electrodialysis. Reverse osmosis constitutes around 60% of global desalination capacity. While in thermal processes, we have the multi-effect distillation and multi-stage flash distillation. Multi-stage flash distillation is the second most popular desalination technology in the world. So let us review the membrane method first, the reverse osmosis method. For understanding the reverse osmosis method, we should first understand the process of diffusion. Osmosis is basically a specialized type of diffusion, and diffusion is the movement of a substance or particles from a region of high concentration to a region of low concentration. In osmosis, two solutions with different concentrations of dissolved solids and dissolved salts, they are separated by a semi-permeable membrane, as shown here in the picture. Osmosis is the natural movement of solvent through the semi-permeable membrane from low concentration of the solvent to the side with a high concentration of the solvent in order to establish an equilibrium. The RO technology is based on the properties of semi-permeable membranes, which can separate water from a saline solution when excess of osmotic pressure is applied on the membrane systems. So reverse osmosis occurs when a force is applied to the site concentrated with the solute, in this case salt, and it causes the water to move towards the less concentrated site of the semi-permeable membrane, thus producing fresh water. The semi-permeable membrane only allows water to flow through, leaving the salts behind. Solar PV powered RO systems are getting very popular these days due to the modularity and easy scalability of both PV and RO elements, while solar thermal RO plants are way behind in terms of commercialization. Many PV based RO systems have been built and field tested, and all of these systems are at community scale, producing between 100 liters and 60 cubic meters of water per day. Let us discuss the key features of reverse osmosis. It is the most common method, as almost 60% of desalination plants in the world are RO plants. Secondly, it's easy and readily available to use. The RO plants can be immediately started or stopped. The RO desalination is also suited and used for small scale plants in rural areas or islands where there is no other water supply available. For example, most desalination plants in the Caribbean area, they use RO systems. Thirdly, typically a seawater RO plant produces 55 to 65 liters of fresh water for each 100 liters of seawater through multiple stages. So we can assume that the overall efficiency of RO plants is around 65%. Moreover, they have low energy consumption of 3.5 to 5 kilowatt hours of electricity per cubic meter of clean water produced. And the ultrafiltration of membranes and renewable energy is making this technology more suitable. Typical seawater salinity, which is suited to RO system, is around 35,000 ppm of dissolved solids. However, in some regions such as Red Sea and the Arabian Gulf, the total dissolved solid content is higher, around 41,000 to 45,000 ppm. In these regions, therefore, seawater leads to high fouling and high surface temperature. Therefore, appropriate feed water pre-treatment is carried out in those areas prior to RO desalination. The pre-treatment of salt water is also required to increase the life of the membranes and to avoid fouling on the membranes. The pre-treatment includes steps such as pre-filtration and anti-scaling treatment. Now let's move on to the second membrane method, which is the electrodialysis method. Um, Electrodialysis separation process basically it works at ambient pressure and utilizes an electric potential to feed salt through an ion selective membrane, leaving fresh water behind. The total dissolved solids are removed from the feed seawater and instead of the reverse, thus making it unique from all other main desalination processes. As the feed water flows through, the negative salt ions pass through the anion porous membrane to a positive electrode, whereas the positive salt ions pass through the cation porous membrane towards a negative electrode. And in the photovoltaic electrodialysis, basically the electrodes are connected to an outside PV source in the container of the salt water, as shown here in the picture. It removes water salinity as water processed through ion selective membranes positioned between two electrodes, as shown in the figure. Due to the energy requirements of the process, electrodialysis is much more cost effective for for lower salinity water, and it is typically implemented for purification only with brackish water resources. So electrodialysis cannot be used for seawater. It can only be used for brackish water available within the land. Currently, electrodialysis accounts for almost 3.6% of global desalination capacity, and it is suitable for TDS of up to 12,000 milligram per liter, and the energy consumption is quite less, 1.5 to 4 kilowatt hour per meter cube for feed water with 1500 to 3500 ppm solids. And the typical plant maximum capacity could be around 45,000 cubic meters per day. Thirdly, then we move on to the thermal methods. Let's first discuss the multi-stage flash method. The solar powered multi-stage flash method is shown in the picture here. It's type of a thermal desalination that involves a solar source to heat salt water between 900 and 90 and 110 degrees centigrade under high pressure. And it is then passed through a series of chambers which are shown here on the picture. The salt water passes through several successive chambers, each with a lower pressure than the preceding one. This results in even more vaporization of salt water called flash. The evaporated water is recollected and recondensed into refined water. The water that did not vaporize exits the system with a higher concentration and is discarded appropriately as waste, while the refined water is discharged into the municipal water supply as potable water. MSF is a frequently used thermal technology in the Middle East and uses fossil fuels for running the plant. The world's largest desalination plants operate on this technology, with their specific energy consumption in the range of 81 to 106 kilowatt hours per cubic meter, for a temperature difference between inlet seawater and hot brine of 10 to 45 degrees centigrade. Currently, MSF accounts for almost 26.8% of global desalination capacity, and the energy consumption is around 80.6 kilowatt hour of heat plus around 2.5 to 3.5 kilowatt hour of electricity per cubic meter of water. The second thermal method is multiple effect distillation, which is called MED. It is basically it includes heating salt water under pressure, which is then made to flow through a series of chambers. The heat for causing evaporation in the first chamber is provided by solar energy or by combustion of fossil fuels, and vapors thus formed are used to heat the feed water in the subsequent chambers. Here in the attached picture, you can see that a solar field is used to heat the fluid in the first chamber, and basically this is in this MED, the solar thermal technologies such as the parabolic parabolic dishes, they can be easily used for heating the water and heating the input feed. However, in this process, the water vapor from each chamber at high pressure is used to heat the water in the subsequent chamber at a lower pressure than the preceding chamber. And this sequence is replicated, resulting in the separation of condensed water vapor and the production of more water vapor as the stages progresses. Now let's look at the pros and cons of MED as compared to MFD. MED, it operates at lower temperatures of approximately 70 degrees centigrade as compared to MSF, which operates at around 110 degrees centigrade. So it helps reduce the tube corrosion and the likely scale formation around the tube surfaces. Secondly, the low pre-treatment and operational costs of MED, they basically are possible because the quality of feed water is not as essential as in the case of RO processes. The power consumption of MED is lesser than that of MSF processes, and we can achieve higher performance efficiency in MED plants as compared to MSF in regards to heat transfer and fresh water production cost. Finally, we'll move towards the third section, which is the solar energy potential in desalination efforts. So, the addition of solar energy sources to desalination efforts can make the process more sustainable. And because the fossil fuel prices are predicted to continue to increase, while the price of solar energy technologies are going to decrease in the immediate future, so that makes a viable business case. There are two major ways solar energy can be utilized in desalination efforts. First is the distillation processes, which are driven by heat produced directly from solar energy systems. And second is the membrane and distillation processes, which are driven by electricity produced by the solar PV systems. The solar energy sources which are utilized in desalination are solar thermal, solar PV, and concentrated solar power. And solar energy can also be used on a case-to-case basis depending on the sources of energy available in a given area. So, for example, in small island states, the RO technology could be used, while in the brackish water areas, the MSF or MED technologies can be easily used. Let's now look at the comparative cost analysis of different desalination technologies. In general, as a matter of principle, desalination based on renewable energy sources is still expensive if compared with conventional desalination, as both investment and generation costs of renewable energy are currently higher. However, under certain circumstances, for example, installations in remote areas where distributed energy generation is more convenient than extending centralized electricity grid for transmission and distribution. So in such areas, renewable energy desalination could compete with conventional systems. As far as capital costs and operation and maintenance cost is concerned, a comparison of two most used conventional desalination systems, that is the RO and MSF, shows that the MSF plants requires higher capital costs, while the RO plants requires higher operation and maintenance costs due to the plant complexity. And as for overall desalination cost, significant reductions have occurred over the past years. But water desalination remains economically affordable only for middle income to higher income countries, and it is very expensive for poor countries. The typical production cost of conventional desalination plants running on fossil fuel is between 1 to 2 US dollar per cubic meter of water produced. However, with the rapid decrease of solar energy costs, the technical advances, and the increasing number of installations, the solar desalination is likely to reduce significantly in cost in the near future, and it could potentially become an important source of water supply for regions affected by water scarcity. Now, we have some technical challenges to solar desalination. The first one is that we need to tailor solar power technologies to basically power the desalination plants. The major issue is that solar power technologies were not originally developed with with the view of powering desalination plants, and instead, generally, they were developed with the goal of providing electrical energy. For example, PV systems, by definition, they convert solar power to electrical energy. Moreover, solar thermal systems, they generally harvest heat energy and convert this heat to electrical energy via steam turbines. And this conversion to electrical energy, it basically includes approximately 40% losses. However, many desalination systems can be powered by pressure or heat energy directly without use of electrical energy. So, as a result, there are considerable technical challenges to adapt solar energy systems in order to power the desalination systems, and the researchers and the industry, they need to find solutions for optimally powering the desalination through solar. The second technical challenge is to avoid the hyperbole and face the challenge head on. For the proper development of cost-effective and energy-efficient solar-powered desalination system, the challenge is not as much technical as it is intellectual. The issue is that promoters, for example, private solar power corporations, they sometimes optimistically overstate the efficiencies and cost efficiency of solar technologies, as well as the solar power desalination systems. As a result, there is an underappreciation of the technical challenges involved to ensure the systems are cost effective and energy efficient. Evidence of this disconnect is that the deployment of some large systems of desalination powered by PV. These large systems are neither cost efficient and nor energy efficient, despite the claims by the project developers. Also, the deployment of solar powered desalination system in remote arid region, it involves considerable risk, requiring considerable R&D into finding the solutions of these problems and risks. The third challenge is a need for better determination of saline and brackish water reserves. Although there is an excellent knowledge of the geographical location in the world with high solar insolation, and we know that where PV and energy resource availability is high and where it's low, but when we come to the desalination systems, we need to have the similar kind of mapping for sources of seawater or brackish water. This is because the desalination of brackish water involves considerably less energy cost. Hence, there is a need for more knowledge of brackish water reserves. And what is needed is a detailed world map of brackish water reserves. Unfortunately, because certain brackish water reserves can be associated with petroleum and natural gas reserves, so the maps of those brackish water reserves are sometimes made proprietary by those exploration companies, and they are not shared with the general population. Finally, we will discuss the idea of solar ponds. The solar energy from the sun is basically absorbed by salt water, which causes the pond to heat off. The ambient air causes the top layer of water to cool off, but the water basically rises from the bottom and the cooler water sinks from the top. And this pond is designed in such a way that the top layer is less dense and therefore less saline, while the bottom layer is denser and more saline. And thermal energy, because the because the salt, it gets collected in the lower zone of the pond, I hope you can hear me now. Apologies for another disconnection. Um, let's quickly move towards the case study of solar water desalination in Al Khafji region in Saudi Arabia. This plant utilizes an ultra high concentrator PV system, and basically there are three phases to the plant. In the first phase, the solar power desalination plant with a capacity of 30 million liters per day will be constructed. In the second phase, the construction of a second solar power desalination plant of around 3000 million liters per day will be constructed. And in the third phase, the construction of additional solar power desalination plants across Saudi Arabia will be carried out. So all these three phases are projected to be completed by 2020, and as a result, Saudi Arabia will become one of the largest producers of desalinated water in the world. And all this desalination technology, this will be driven by solar PV based generation. Now let's move towards the conclusions of this presentation. So solar thermal, it can either be direct or indirect. The direct solar thermal, it basically condenses and collects the water into a one unit, while in indirect solar thermal condenser, the condenser is connected externally to the collectors. The direct systems are relatively low cost and simple to construct, the example being solar still, but they of course require large area of land and they have low freshwater production. As discussed earlier, they are ideally suitable for the rural areas because the land availability is large and the population is generally, dispersed over a large area. In urban areas, the electrodialysis was the recommended technology. Within indirect systems, MED and MSF are able to produce greater quantities of fresh water, but of course they have a higher capital cost. Um, Secondly, solar panels can be used to generate electrical energy, which can be used for the RO process. As Mr. Bilal in his presentation earlier explained, RO process is generally the cheapest technology for solar desalination right now. Um, the fluctuations in the power generation, they can also be expected as the input of solar energy can change with the weather. And as a result, the power fluctuations could decrease the efficiency of the RO process. However, the battery storage could be introduced, which could deal with these fluctuations. Finally, thank you very much for this presentation. Despite so many interruptions and disruptions, we again apologize for the frequent internet disconnections, and we hope that you did not miss out on any important details. Let's move on towards the questions. Uh, the first question is, does desalination process also remove essential minerals for the water too? This question is has been asked by Mr. Essen. So basically, there are various desalination technologies when we consider the RO desalination. So within the RO desalination process, the essential minerals of the water, basically they are removed in ultra high RO plants. For example, if we take the example of these water bottlers, which provide mineral waters, so in those plants, the ultra high capacity RO with is used. Basically, it strips the water of all kinds of mineral, and later on, when the within the output, the minerals are added separately as per the specifications of that particular company. So that is the case with mineral water, but in desalination processes which are carried out for general population, we can always choose the membranes of such sizes which could allow the essential minerals for the water. So it depends on the type of the application, but generally in RO, the reverse osmosis, the essential minerals are stripped off, while in other desalination technologies, that's not the case. The second question is there any distinctive order in the purified water? So basically, in all the desalination technologies, the indirect desalination technologies which you mentioned, the pre-treatment and the post-treatment of the water is carried out. Generally, the charcoal filters are used in order to, if there is any distinctive color in the water, that color is removed through charcoal filters. If there is any distinctive odor, that is also used through those filters. Um, Thirdly, the cost comparison of producing water from RO and solar still. So I guess we have gone through this in one of the slides. Let me go through here again. So the comparative cost analysis of all the solar desalination technologies is provided in this table here. This table is basically taken from International Energy Agency, and here the comparison of RO and solar still can be carried out. The water cost for solar still, it's been given as anywhere between 1.3 to 6.5 US dollars per cubic meter of water produced. Of course, it depends on, as we discussed earlier, there are different varieties within solar stills. So it depends on the kind of solar still which you are using, its size, and the kind of material used for constructing the solar still. But generally, the given range is 1.3 to 6.5 US dollars of cubic meter. Um, for solar reverse osmosis, there are different ranges given. Uh, for brackish water, the cost is between 6.5 to 9.1 US dollar per cubic meter, and for seawater, the cost is 11.7 to 15.6 dollars per cubic meter. So clearly, the on a cost comparison on a per cubic meter of water produced, the reverse osmosis systems, they are much more expensive as compared to solar stills. But then again, it all depends on the type of application. If the amount of water required is very less, and you need to provide water to let's say an island state with a population of less than 100 people and large area, then solar stills can easily be used. But if water is to be provided to a population of, let's say, around 1,000 people and more than 1,000 people, solar still would not make a viable business case, as a large area would be required to achieve that kind of water supply. In those cases, reverse osmosis is one of the better technologies, and because the as compared to MED or MSF, the reverse osmosis PV, it is currently in the application stage, while other technologies are currently in R&D stages. So it varies on case-to-case basis. Let me check if we have some more questions. So yeah, we are done with the questions. If you have any more questions, so feel free to write those in the form of email. We'd be glad to answer the provide answers to your questions. Secondly, this particular webinar, basically it's a series of two webinars. So in the first webinar, we covered the overall technical aspects of solar water desalination, as well as their applicability to different scenarios. In the second webinar in this series, we will be concentrating solely on the South Asian region and the SAARC region. And we would be inviting experts who could speak about their experience within the region and the applicability of various solar desalination technologies within the region. So we'll be announcing the dates for the second webinar soon, and this webinar was basically setting the stage for the second webinar. The essential basic overview has been provided, and we hope that you join us for the second webinar as well, so that we could have special experts on board who could answer your questions and who could clear your concepts regarding the applicability of solar desalination in our South Asian context. So with this, I would like to conclude our webinar. Thank you everyone for attending today's session of the webinar. We listened to an excellent presentation delivered by Mr. Bilal Hussain regarding the applicability of solar desalination for island states. All these presentations, they would be available on SAARC Energy Center's website very shortly. The website is www.saarcenergy.org. We would love to hear from you any suggestions or comments for further improvement. Moreover, any suggested topics of interest on which you would like us to arrange future webinars, we would gladly do that and we would welcome your suggestions. Once again, I would like to apologize for interruptions and frequent disconnections. We will try to minimize that in coming webinars. With this, I would like to sign out and thank you once again for joining us today, and I look forward to seeing you next time. Thank you and goodbye.